Chemistry, as understood today, is a relatively modern discipline that evolved from ancient pursuits. Two major quests drove early chemical exploration: the search for the Philosopher's Stone, believed to transform base metals like iron and copper into gold, and the quest for the elixir of life, which was thought to grant immortality. These pursuits laid the groundwork for what would eventually develop into the field of chemistry. In ancient India, the discipline of chemistry was known as Rasayan Shastra, encompassing a wide array of practices including metallurgy, medicine, and the manufacture of cosmetics. The knowledge of chemical processes was not only theoretical, but was applied practically in various aspects of daily life. Systematic excavations at Mohenjo-daro in Sindh and Harappa in Punjab provide compelling evidence that the story of chemistry's development in India is ancient and rich. Archaeological findings reveal that baked bricks were utilized in construction, indicating an understanding of materials and their properties. The mass production of pottery, regarded as one of the earliest chemical processes, involved mixing materials, molding them, and subjecting them to heat to achieve desirable qualities. The remains of glazed pottery found in Mohenjo-daro and the use of gypsum cement in construction work demonstrate advanced chemical knowledge. Gypsum cement, composed of lime, sand, and traces of calcium carbonate, showcases the ability of ancient Indians to manipulate materials for construction. The Harappans also produced faience, a type of glass used in ornaments, and they melted and forged various metals, including lead, silver, gold, and copper. Techniques for improving the hardness of copper by alloying it with tin and arsenic were also developed, showcasing a sophisticated understanding of metallurgy. The archaeological evidence indicates that copper metallurgy in India dates back to the beginning of Chalcolithic cultures in the subcontinent. Numerous archaeological sites support the view that technologies for the extraction of copper and iron were developed independently in India. The Rig Veda, one of the oldest texts in the world, mentions practices such as leather tanning and dyeing of cotton, further illustrating the advanced chemical knowledge of ancient Indians. The golden gloss of black polished ware from northern India remains a chemical mystery that has yet to be replicated. These wares indicate a mastery of kiln temperature control, essential for achieving specific material properties. Kautilya's Arthashastra even describes the production of salt from seawater, demonstrating an understanding of chemical processes in everyday life. A vast number of statements and materials described in ancient Vedic literature align with modern scientific findings. Archaeological discoveries of copper utensils, iron, gold, silver ornaments, and terracotta discs in northern India highlight the advanced metallurgical practices of the time. The Sushruta Samhita, an ancient medical text, emphasizes the importance of alkalis, while the Karaka Samhita mentions the preparation of various acids, including sulfuric and nitric acids, as well as oxides of copper, tin, and zinc. The preparation of gunpowder mixtures is documented in the Rasopanishada, showcasing the advanced chemical knowledge of ancient Indian scholars. Tamil texts also describe the creation of fireworks using sulfur, charcoal, saltpeter, mercury, and camphor, indicating a sophisticated understanding of explosive materials. Nagarjuna, a prominent Indian scientist, was a reputed chemist, alchemist, and metallurgist. His work, Rasratnakar, delves into the formulation of mercury compounds and discusses methods for extracting metals such as gold, silver, tin, and copper. The Rasanavam, a text that appeared around 800 CE, elaborates on the uses of furnaces, ovens, and crucibles for various purposes, including metal identification through flame color. Chakrapani made significant contributions to the field by discovering mercury sulfide and inventing soap using mustard oil and alkalis. The production of soap in India dates back to the 18th century, utilizing ingredients like oil of aranda and seeds of the mahua plant, along with calcium carbonate. The vibrant paintings found on the walls of Ajanta and Ellora, which have remarkably retained their colors over centuries, testify to the high level of scientific achievement in ancient India. Varahamihir's Brihat Samhita, composed in the 6th century CE, serves as an encyclopedia that informs about the preparation of glutinous materials used in construction, derived entirely from plant extracts, concentrated through boiling and treated with various resins. Numerous classical texts, such as the Atharva Veda, mention dye substances including turmeric, madder, sunflower, orpiment, cochineal, and lac. Other substances with tinting properties like kampochika, patanga, and jatuka are also referenced. Varahamihir's Brihat Samhita provides insights into perfumes and cosmetics with recipes for hair dye made from plants like indigo and minerals such as iron powder and black iron. By the 17th century, paper was known in India, as documented by the Chinese traveler Itzing. Excavations at Taxila indicate that ink was used in India from the 4th century, with colors derived from chalk, red lead, and minimum. The process of fermentation was well known, as evidenced by references in the Vedas and Kautilya's Arthashastra to various types of liquors. The concept that matter is composed of indivisible building blocks emerged in India centuries before modern atomic theory. Acharya Kanda, born around 600 BCE, was the first proponent of the atomic theory, formulating the idea of very small, indivisible particles he termed paramanu, akin to modern atoms. This rich history highlights the profound contributions of ancient Indian chemistry to the scientific world, showcasing a legacy of knowledge that laid the foundation for future advancements in the field. Particles in solids are tightly packed in an orderly arrangement, which restricts their movement. This close proximity gives solids a definite shape and volume. The particles vibrate in place, but do not move freely, resulting in a rigid structure. In liquids, particles remain close together, but can flow past one another, allowing them to take the shape of their container while retaining a definite volume. This fluidity is due to the weaker intermolecular forces compared to solids. In contrast, gases have particles that are spaced far apart, enabling rapid movement and expansion to fill the entire space of their container. The arrangement and movement of particles in each state lead to distinct characteristics across the 3 states of matter. Solids possess a definite volume and shape, making them easily identifiable. For example, a cube of ice maintains its shape until it melts. Liquids, on the other hand, have a definite volume, but no fixed shape. They conform to the shape of their container, as seen when pouring water into different vessels. Gases lack both definite volume and shape, expanding to occupy the entire space available. This behavior can be observed when a balloon is filled with air. The gas expands to fill the balloon completely. These states of matter can transform through changes in temperature and pressure. Heating a solid typically converts it into a liquid, a process known as melting. For instance, ice melts into water when heated. Further heating changes the liquid into gas through evaporation. Conversely, cooling a gas condenses it into a liquid. a process called condensation. For example, water vapor in the air can condense into droplets on a cold surface. The liquid can then freeze back into a solid, completing the cycle. Matter can be classified into pure substances and mixtures. A pure substance consists of identical particles, meaning all the particles have the same chemical composition. Examples of pure substances include elements like gold and silver, as well as compounds like water and glucose. In contrast, a mixture contains various types of particles. Mixtures can be homogeneous, where components are uniformly distributed, such as in a sugar solution or air. In homogeneous mixtures, the individual components are not visible, and the mixture appears uniform throughout. Heterogeneous mixtures, however, have visibly different components. For example, a mixture of sand and salt shows distinct grains of each substance. Other examples include salads or trail mixes, where individual ingredients can be easily identified. The composition of mixtures can vary, as they can contain different ratios of their components. Physical methods can separate the components of mixtures. Techniques such as hand-picking, filtration, and distillation are commonly used. For instance, sand can be separated from salt water through filtration, where the sand remains on the filter paper while the salt water passes through. Pure substances, on the other hand, have fixed compositions. For example, copper, silver, gold, water, and glucose are all pure substances. Glucose specifically contains carbon, hydrogen, and oxygen in a specific ratio, ensuring its composition remains consistent. Pure substances can be further divided into elements and compounds. Elements consist of only one type of atom, existing as either individual atoms or molecules. Examples of elements include sodium, copper, and hydrogen. Different elements have unique atomic structures, with some existing as single atoms, while others form molecules from two or more atoms. For example, hydrogen gas consists of diatomic molecules, where two hydrogen atoms bond together. Compounds form when atoms of different elements combine in a definite ratio. These compounds cannot be separated by physical methods, but require chemical processes for separation. Common examples of compounds include water, ammonia, and carbon dioxide. A water molecule consists of two hydrogen atoms and one oxygen atom, while carbon dioxide contains one carbon atom and two oxygen atoms. The ratio of atoms in compounds is fixed, which defines their unique characteristics. The properties of compounds differ significantly from those of their constituent elements. For instance, both hydrogen and oxygen are gases, but when combined to form water, the result is a liquid. Interestingly, hydrogen burns with a pop sound. Oxygen supports combustion, yet water serves as a fire extinguisher. This transformation illustrates how the combination of elements can lead to entirely new properties. Understanding the states of matter and the classification of substances provides valuable insight into the physical world. This knowledge is essential for various scientific applications, including chemistry and material science, and enhances comprehension of everyday phenomena. The interplay between temperature, pressure, and particle arrangement shapes the materials encountered daily, influencing processes from cooking to industrial applications. Recognizing the differences between pure substances and mixtures is crucial in fields such as pharmaceuticals and environmental science. The ability to separate mixtures through physical methods is vital in laboratories and industries, ensuring the purity and quality of products. For example, in pharmaceuticals, the purity of compounds is essential for effective medication. The classification of matter into elements and compounds allows scientists to explore and manipulate materials at the atomic level. This exploration leads to advancements in technology, medicine, and sustainable practices. The unique properties of compounds derived from their atomic composition drive innovation in creating new materials with specific functions. In summary, the states of matter, solid, liquid, and gas, are defined by particle arrangement and movement. The classification of matter into pure substances and mixtures reveals the complexity of materials in the world. Understanding these concepts is vital for scientific progress and everyday applications, shaping the future of technology and environmental sustainability. This knowledge empowers individuals to appreciate the intricate nature of matter, fostering curiosity and encouraging further exploration in the fascinating realm of science. Every substance possesses unique properties that define its characteristics and behavior. These properties can be categorized into two main types: physical properties and chemical properties. Understanding these properties is essential for scientists and researchers, as they provide insights into how substances interact with one another and their environments. Physical properties are attributes that can be observed or measured without altering the identity or composition of the substance. Common examples of physical properties include color, odor, melting point, boiling point, density, and solubility. For instance, the color of a substance can be seen without changing what the substance is. Similarly, the melting point indicates the temperature at which a solid becomes a liquid, while the boiling point indicates the temperature at which a liquid turns into vapor. Density, defined as mass per unit volume, helps in identifying substances and understanding their behavior in different states. On the other hand, chemical properties describe a substance's potential to undergo chemical changes and transformations. These properties can only be observed when a chemical reaction occurs, resulting in the formation of new substances. Examples of chemical properties include reactivity with acids and bases, combustibility, and oxidation states. For example, when iron reacts with oxygen, it forms rust, demonstrating its reactivity. Similarly, combustibility refers to a substance's ability to ignite and burn in the presence of oxygen, as seen in materials like wood and gasoline. The distinction between physical and chemical properties is crucial in scientific investigations. Physical properties can be measured or observed without causing any change to the substance itself, making them easier to study. In contrast, measuring chemical properties necessitates a chemical change, which can complicate the analysis. Quantitative measurements of physical properties are particularly important for scientific research and experimentation. Many properties of matter, such as length, area, volume, and mass, are quantitative in nature. These measurements are expressed as numbers followed by units, allowing for precise communication of results. For example, the length of a room might be represented as 6 meters, where 6 is the numerical value, and m denotes the unit of measurement. Historically, 2 different systems of measurement were used worldwide: the English system and the metric system. The English system, commonly used in the United States, employs units such as feet, pounds, and gallons. In contrast, the metric system, which originated in France in the late 18th century, is based on the decimal system and is more convenient for scientific applications. The metric system's simplicity and ease of conversion led to its widespread adoption in many countries. Recognizing the need for a common standard system, the scientific community established the International System of Units, SI, in 1960. The SI system provides a unified framework for measurements, facilitating international collaboration and communication in scientific research. The SI system consists of 7 base units, each representing a fundamental physical quantity. 1. Length. The SI unit of length is the meter m. It is defined based on the fixed numerical value of the speed of light in a vacuum, which is approximately 209,792,158 meters per second. 2. Mass. The SI unit of mass is the kilogram, kg. It is defined using the fixed numerical value of the Planck constant, which is approximately 6.62607015 after 10^34 when expressed in joules per second. 3. Time. The SI unit of time is the second s. It is defined based on the fixed numerical value of the cesium frequency, specifically the hyperfine transition frequency of the cesium-133 atom. 4. Electric current. The S unit of electric current is the ampere, A. It is defined using the fixed numerical value of the elementary charge, which is approximately 1.60116634 as 10 to 19 coulombs. 5. Thermodynamic temperature. The SI unit of thermodynamic temperature is the Kelvin, K. It is defined using the fixed numerical value of the Boltzmann constant, which is approximately 1.380649 plus 10 or 23 joules per Kelvin. 6. Amount of substance. The SI unit of amount of substance is the mole, mole. 1 mole contains exactly 6.02146 elementary entities, known as Avogadro's number. 7. Luminous intensity. The SI unit of luminous intensity is the candela CD. It is defined based on the fixed numerical value of the luminous efficacy of monochromatic radiation of a specific frequency. These 7 base units serve as the foundation for deriving other physical quantities such as speed, volume, and density. Understanding these units and their definitions is crucial for scientists, as they provide a standardized way to communicate measurements and findings. In summary, the physical and chemical properties of matter play a vital role in the study of substances and their interactions. Physical properties can be observed without changing the substance, while chemical properties require a chemical change for measurement. The establishment of the International System of Units has further enhanced scientific communication by providing a common framework for measurements. By understanding these concepts, researchers can effectively explore the complexities of matter and contribute to advancements in science and technology. Mass and weight are fundamental concepts in science that are often misunderstood, yet they play a crucial role in various scientific disciplines. Understanding the distinction between these two terms is essential for accurate scientific communication and experimentation. Mass refers to the amount of matter contained in a substance, while weight is defined as the force exerted by gravity on that mass. This distinction is critical, as mass remains constant regardless of location, whereas weight can vary depending on the gravitational pull experienced in different environments. For example, an object with a mass of 1 kilogram will always have that same mass, whether it is on Earth, the Moon, or in space. However, its weight will change based on the gravitational force acting upon it. On Earth, that same 1 kilogram object weighs approximately 9.81 newtons due to Earth's gravity. On the Moon, where gravity is weaker, the same object would weigh only about 1.62 newtons. This variability in weight underscores the importance of using the correct terminology in scientific contexts. In laboratory settings, mass is typically measured using an analytical balance, a highly sensitive instrument that can determine mass with great precision. The standard unit of mass in the International System of Units, SI, is the kilogram. For practical purposes, especially in chemistry, where smaller quantities of substances are often used, grams are the preferred unit of measurement. 1 kilogram is equivalent to 1,000 grams, making it easier to work with smaller amounts of chemicals in experiments. Volume is another fundamental property in science, defined as the amount of space occupied by a substance. Volume is measured in cubic units, and in the SI system, the unit for volume is the cubic meter. However, in laboratory practices, smaller volumes are frequently expressed in cubic centimeters or decimeters. This is particularly relevant in chemistry, where precise measurements of liquids are often required. A liter, although not an SI unit, is a common measurement for liquids in laboratory settings. 1 liter is equivalent to 1,000 milliliters, and 1,000 cubic centimeters equals 1 cubic decimeter. This makes the liter a convenient unit for measuring liquid volumes, especially when dealing with solutions and reagents in chemical experiments. To measure liquid volumes accurately, scientists utilize various tools, including graduated cylinders, burettes, and pipettes. Each of these instruments is designed for specific tasks, ensuring that measurements are both accurate and reliable. A graduated cylinder is typically used for measuring larger volumes of liquids, while a burette allows for precise dispensing of liquid in titrations. Pipettes are used for transferring small volumes of liquids with high accuracy. Additionally, volumetric flasks are employed to prepare solutions of known concentrations, ensuring that the volume of the solution is accurate for experimental purposes. Understanding how to use these tools effectively is essential for anyone working in a laboratory environment. Density is a critical property that connects mass and volume, defined mathematically as the mass of a substance divided by its volume. The formula for density is expressed as density E mass / volume. The SI unit of density is kilograms per cubic meter, but in chemistry, it is often more practical to express density in grams per cubic centimeter. This conversion allows chemists to work with smaller quantities of substances more easily. Density provides valuable insights into the physical properties of substances. A higher density indicates that the particles within a substance are packed more closely together, while a lower density suggests that the particles are more spread out. This property can influence various characteristics of materials, including buoyancy, solubility, and thermal conductivity. For instance, substances with higher densities tend to sink in liquids with lower densities, which is a principle that can be observed in everyday life, such as when oil floats on water. Temperature measurement is another essential aspect of scientific inquiry, utilizing 3 primary scales: Celsius, Fahrenheit, and Kelvin. The Kelvin scale is the SI unit for temperature and is widely used in scientific contexts. Celsius thermometers are calibrated from 0 to 100 degrees, with these 2 temperatures marking the freezing and boiling points of water, respectively. The Fahrenheit scale, commonly used in the United States, ranges from 32 to 212 degrees. The relationship between the Celsius and Fahrenheit scales can be expressed with the formula Fahrenheit = 9 to 5 x Celsius plus 32. This equation allows for the conversion of temperatures between the 2 scales. Additionally, the Kelvin scale relates to the Celsius scale through the equation. Kelvin equals Celsius 273.5. It is important to note that while negative temperatures are possible in the Celsius scale, they cannot occur in the Kelvin scale, emphasizing the absolute nature of this temperature measurement. In conclusion, a solid understanding of mass, weight, volume, density, and temperature is essential for professionals in scientific fields, particularly chemistry. Accurate measurements and clarity in these terms are vital for conducting experiments and achieving reliable results. Mastery of these concepts not only enhances scientific literacy, but also fosters a deeper appreciation for the intricate relationships that govern the physical world. By grasping these fundamental principles, scientists can communicate more effectively and contribute to advancements in their respective fields. Every experimental measurement inherently carries uncertainty due to limitations in measuring instruments and the skill of the individual conducting the measurement. For instance, a platform balance may indicate a mass of 9.4 grams, while an analytical balance provides a more precise measurement of 9.4213 grams. In this scenario, the digit 4 in the platform measurement represents an uncertain value, underscoring the importance of understanding significant figures in scientific measurements. Significant figures are essential for conveying the certainty of measurements. They consist of all known digits plus one estimated digit. For example, in the measurement of 11.2 miljoule, the digits 11 are certain, while the digit 2 is uncertain, with an understood uncertainty of +1. This concept is crucial for scientists and researchers, as it enables effective communication regarding the precision of their measurements. There are specific rules for determining the number of significant figures in a measurement. The first rule states that all non-zero digits are significant. For example, in 285 cm, there are 3 significant figures, while in 0.25 ml, there are 2 significant figures. The second rule pertains to leading zeros, which are not significant, and serve only to position the decimal point. Thus, in the number 0.03, there is only one significant figure, represented by the digit 3. The third rule indicates that zeros between non-zero digits are significant. Therefore, in the number 2.05, there are 4 significant figures, 2, 0, 0, and 5. The fourth rule addresses trailing zeros, which are significant only when they appear to the right of a decimal point. For instance, in the measurement of 0.200 G, there are 3 significant figures, whereas in the number 100, there is only 1, unless a decimal point is specified. Counting numbers, such as 2 balls or 20 eggs, possess infinite significant figures because they are exact. In scientific notation, all digits are considered significant. For example, the number 4.02 has 3 significant figures. Precision refers to the closeness of repeated measurements, while accuracy indicates how closely a measurement aligns with the true value. When performing mathematical operations, specific rules apply. For addition and subtraction, the result cannot have more decimal places than the original numbers. In contrast, for multiplication and division, the result must match the number of significant figures in the least precise measurement. Rounding rules are important when adjusting numbers to meet significant figure requirements. If the digit to be removed is greater than 5, the preceding number increases by 1. If it is less than 5, the preceding number remains unchanged. Dimensional analysis is a method used to convert units from one system to another ensuring accurate calculations in scientific work. In summary, understanding significant figures and dimensional analysis is vital for ensuring precision and accuracy in scientific measurements. By adhering to these established rules, researchers can effectively communicate their findings and maintain the integrity of their data.